normally I would just say just because it's required. But to not sound like such a slacker, it's because I want to use math to find out if something is true or not.
That's an interesting reason. I guess it does allow us to figure out if there are differences between groups, like if a treatment really works or not.
For example, t-tests are one way to test to see if there is a difference between groups.
Right, all inferential stats do this, but independent sample t-test is a specific test that allows us to find out if there's a difference between two groups.
Okay, so what exactly is a t-test?
The t-statistic measures the distance between a data point and a population mean in terms of standard errors.
Hold up. Measuring distance in terms of standard error. That sounds like z-score.
Yeah, t-scores are very much like z-scores, but we're using standard error as a unit of measurement instead of standard deviation.
Isn't a standard error a type of standard deviation? Isn't it the standard deviation of a sampling distribution?
What the heck? Back it on up. What is a sampling distribution? Is that the same thing as a sample?
Oh, you really have to know sampling distribution before you can understand inferential test. Well, you probably know what a sample and the population is, right?
You're supposed to draw samples randomly from a greater population.
Great. Then imagine taking a random sample of a known population and computing a sample statistic like the mean. Imagine doing it over and over again until you have a whole bunch of means. All those means would constitute the sampling distribution of the mean, or
Oh, it's a distribution of a bunch of samples, or more precisely, the distribution of all possible samples from that population.
okay, so the standard error is the standard deviation of that sampling distribution of means. It's just a mouthful to say, so it's easier just to say standard error.
So that's where the central limit theorem comes in, right? That gives you the formula for standard error.
True, but do you know why the CLT exists?
Uh, to give me more stuff to memorize? Just kidding. I know it must have something to do with this sampling distribution.
Yes, the point of the CLT is that it would be nice to know the distribution of all possible samples of a particular population.
But that would take a long time to simulate, no?
By hand, yes. But mathematicians have figured out that there is a systematic relationship between a population and the sampling distribution of the mean.
Oh, yeah, I have the CLT memorized, but let me see if I could connect what I know with what you are telling me. I know the CLT says that 1, the shape of sampling distribution is roughly normal, no matter what the shape of the population is, and the mean of the sampling distribution is the same as the mean of the population, and the standard error depends on the sample size. Specifically, the standard error is equal to the population standard deviation divided by the square root of a sample size.
Whoa, impressive that you have that memorized. But let's think about it more broadly. It seems like you're talking about the shape, center, and spread of the sampling distribution.
Oh, right. That's an easier way to remember the 3 points. And it seems that all three talk about the relationships between the population and the sampling distribution, just like you said. But how does the t-test relate to all of this?
Well, we often don't know the standard deviation of the population, so we use an estimate of it that we created from the sample. When we do that, the sampling distribution isn't quite normal. It's almost normal. Its shape is a t-distribution instead.
So that's where the t in t-test comes from. T for t-distribution.
When we are conducting a t-test, we're interested in the difference of means. If the difference of sample means are large, then there is a very low probability of getting such an extreme difference, given that the null hypothesis is true.
Oh, so I guess the null hypothesis of all t-tests is that the difference between the means of the two groups is zero. Just like saying that the means are equal. Is zero the center of the sampling distribution then?
Yes, so you want to know whether the difference between two groups is close to zero or far from zero. If the difference is close to zero, then the two groups are very, very similar.
Okay, so I can see that That's why we need a t-statistic. If we are many standard errors away from zero, then our t-statistic is either very positive or very negative. Very extreme, as you put it.
Right. That's where the third point of the CLT comes in.
That's the standard error, is the estimated standard deviation of the population divided by the square root of the sample size.
So, what's the standard error like if the sample size is huge?
It would be very small.
And if your ruler is very small, then more of those can fit in the distance between the sample difference and zero.
So a small SE makes it seem like the sample is very far away from zero relative to a big SE.
You got it. So now let me give you an example to use with a T statistic. Let's just say if we're trying to figure out our treatment group, let's say the happy drug group is different from the control group that did not get the happy drug.
I guess if there is a big difference between the mean happy score of the drug group versus the control group, I can conclude that we can reject the null hypothesis.
Well, you can't just take the raw difference. You have to look at the difference measured in terms of standard error, because the people in each group are not equally happy.
Ah, that's why measuring in terms of variability is important. If people were similarly happy, then our unit of measurement, the SC, would be small. And even small differences in means would appear big.
Right. If you have a big T statistic, it tells us that our treatment significantly changed the happiness level of people. Perhaps they end up significantly happier than the control group.
But so far, we've only been discussing independent sample t-test, right? Where we're just interested in two different groups of people.
Right? Hmm. I can't remember what the other kind of t-test is called.
Oh, it's a within subjects or paired sample t-test because they are the same people. They just got tested 2 times.
Okay, so if I were doing the happy drug test as a within subject test, instead of comparing my happy drug group to a control group, I would compare the drug group's happiness score before and after taking the drug?
Yes, that's one way of doing a within subjects design. But if you look at the formulas for t-statistics for those two different t-tests, they are subtly different.
Let me see. Independent sample T formula is like this, and the paired sample T formula is like that.
So here, for within subject t-test, instead of just finding the means for the pre and post scores as if they are separate groups, you find the mean of the differences.
Man, so it's the mean of the difference versus the difference of two sample means? It's like the same word said in different order.
Yes, but they mean different things once you switch the order of the words. Finding the difference between the before scores and the after scores before finding the mean of those differences preserves the pairing of the scores.
Oh, but in the independent samples T, since they are totally independent groups of scores, we just find the means of the groups first, before finding the difference between them. It also seems like the standard error are different.
Right. Here you find the standard error differences, which is the standard deviation of sample differences divided by the square root of n.
Whoa, how is the standard error of difference different from standard deviation of differences? Mind-blowing.
Hey, right, this is confusing. You really have to know this well in order to see that there is an important difference between them.